is Paulo Tabuada, who is a VJ K-Dir Professor of Engineering. So Paulo's contributions to control and cyber systems have been recognized by multiple awards, including the Career Award in 2005, the Donald P. Ekman Award in 2009, the George Axelby Award in 2011, the Antonio Ruberti Prize in 2015.
Sorry, Colin, you are still sharing.
Sorry?
You are still sharing.
Checking out the audience.
Yeah. Paulo has been the chair and general chair for several conferences. He is also HSCC steering committee chair and served as editorial board in IEEE embedded systems letters, the IEEE transactions of automatic control. So Paulo, you are now, it's your floor. Kalin just cleared up for you.
I finally managed to stop sharing. Thanks, Mismi.
Let's see if this thing works.
Yeah, we can see your screen.
Can you see it now in full screen?
Yes, yes, yes.
Okay, all right. So what I'm going to do with this talk is just give you a few highlights of something we've been working for the past, I don't know, 7 or 8 years on trying to reason about robustness in cyber physical systems. But the most challenging part is really thinking of robustness in discrete systems, if you want to. And if you want, think of discrete systems as software systems. And so if I want to convince you that robustness is important, I have to give you some way of defining what robustness is. And here's one definition coming from the IEEE Glossary of Software Engineering. It says that it's the degree to which a system or component can function correctly in the presence of invalid inputs or stressful environmental conditions. Depending on your background, if you're coming from control, you think of these invalid inputs as disturbances. If you're coming from a computer science background, you may want to think these are violations of environment assumptions. The system you design has to work in a certain environment. You make certain assumptions about the environment when you design it. Well, but when you deploy it, those assumptions are going to be violated, and you still want your system to do something reasonable, ideally something good. So the idea of robustness and ways of reasoning and formalizing it has been around for quite some time. So let me tell you how people think about robustness in control theory. And the modern way of looking at robustness was introduced in 1989 by Eduardo Sontag, and in particular introduced this notion of input to state stability. And so what is the desired behavior in this case? That the solution of the differential equation stays at 0, starts and stays at 0 for all time. And what's the environment assumption? There are no disturbances. Here, the disturbances are represented by that D letter on the differential equation. So if we start at the origin and D is equal to 0, we stay at the origin forever. That's the objective. Now, it came up with this way of defining ISS, given by that inequality that you see up there. I'm not going to describe it. I'm just going to mention that it captures 2 properties described at the bottom of the slide. First, that small changes in the assumption, that is, if the disturbance instead of being 0, it becomes non-zero but small, will force the state not to be at the origin, but close to the origin. In other words, a bounded disturbance leads to a bounded consequence. That is, it's not the case that a small disturbance will lead to a catastrophic consequence. And the second is that even if there are disturbances, as soon as they disappear, the system recovers and therefore comes back to the original operating point. Now, if I want to explain this with a picture, in red we see the solution of the differential equation, that it's supposed to converge to the blue point, which is the origin, and it's not converging because there is a disturbance, but because the disturbance is small, it doesn't deviate too much from the blue dot. So small disturbances, small consequences. Of course, if at some point the disturbances disappear, the system is supposed to recover. And that's what happens. Disturbances disappear, the system returns back to its operating point. Now, the very same notion had been introduced in computer science 20 or 30 years before. in a very nice paper by Dijkstra, like a 2 or 3 page paper, where it talks about the notion of self-stabilization. It also has a formal definition, and I'm not going to go through the formal definition. Again, I'm going to give you a picture and show that it captures exactly the same that had been discovered in control theory 20 or 30 years later. So here in blue, what I'm showing is the desired behavior. This is what the system should be doing, staying in that blue region of states. Now, if a disturbance occurs, here denoted by the red transition, the system will move away from the blue region, but will always be captured in the gray region. Again, this notion that small disturbances should have small consequences. Here, bounded disturbance will have bounded consequences. As long as there are disturbances, these are the red transitions, the system stays in the gray region. But if the disturbances disappear, then the system recovers and goes back to the blue region, exactly like the definition in control. So independently, this idea that small disturbances should have small consequences and absence of disturbances should let the system recover is what people intuitively think of robustness. Now, depending on the framework, depending on the setting, the framework may be different, the formalization may be different, but completely different communities thought about the same concept. So we took this as our starting point, and we wanted to then take this notion as a notion of robustness and see how we could use it for cyber-physical systems. Now, there's one important difficulty here, is that in both of these notions, the desired behavior, the nominal behavior, corresponds to a safety property. Staying in a given set of states or staying at the origin is a safety property. Things become much more challenging when you want to define robustness for a liveness property, because this notion of recovering is no longer trivial. There's no set of states you're supposed to return to. If you think in topological terms, now safety properties correspond to closed sets, but liveness properties correspond to dense sets. There's no notion of distance to a dense set. There's no notion of convergence. Things become much more challenging. So what we did instead was, well, let's use temporal logic as a way of trying to extend these notions of robustness to get something a little bit more interesting that would also capture liveness properties. Now, today, I'm only going to talk about the fragment of LTL that only has always and eventual operators, blocks and diamond, but we did the work for a full LTL, but here I'm just going to focus on this case because it's easier to describe. And let me try to capture the notion of robustness we had before. So because we were dealing with the nominal behavior were safety properties, let's say that the assumption is always P. P is an atomic proposition, so that's a safety property. Under that assumption, we should have always Q. Now, how do I capture the fact that once disturbance disappear, once the assumptions that were violated now start being enforced, the system recovers? Well, I simply weaken the assumption from always P to eventually always P. And then, rather than not being able to claim anything about the consequence, as it would be the case in classical logic, I'm going to say that because I weakened the assumption, I still want a weakened version of the guarantee to hold true. And the weakened version of the guarantee will be eventually always Q. So you can think that eventually always P is the assumption at some point becomes satisfied, and therefore at some point the guarantee will become satisfied. Now, this captures what we saw before, but how do we go beyond that? Can we keep on weakening assumptions and weakening guarantees to get, handle robustness for a larger class of properties? And in logical terms, this has to do with which truth value will I give to always P? So always P being satisfied means that P has to be true all the time. That's the picture at the top. Eventually, always, I think of it as always P with a delay, provided that I discard some initial prefix, then I really have always P. Can I further weaken this? And yes, I could say that instead of having P satisfied with a delay, it will be intermittently satisfied. So it's still satisfied infinitely many times, but now violated infinitely many times. Even worse than that, if it's satisfied just finitely many times. And even worse than that is that if it's never satisfied. What does this mean in logical terms? That I really think of the top picture as being true, always P is true, but now all these different ways in which always P is violated, now they correspond to different shades of false. And clearly I have a preference among them. I should not treat all of them as being the same as it's done in LTL. In LTL, all of these simply mean false. Now I want to assign different truth values, and it will be convenient to think of them as tuples of 4 bits. And I have a clear preference among them. 0, 1, 1 is preferable over all the others. But if I don't have 0, 1, 1, 1, then I prefer that it's satisfied infinitely many times. And if not, then I get to 0, 0, 1, and so on and so forth. So what it suggests is that I take this set of truth values that is linearly ordered according to my preferences. And then I want to build a logic that uses these as my set of truth values. Now, this will be a many-valued logic. I will have 5 different truth values. And when we define the semantics of a logic with many truth values, the algebraic structure you need to have on your set of truth values is called the residuated lattice. So it's a lattice so that you have Boolean operators. And it has this operation of residue, which lets us define implication. And so once we figure out that this is what we wanted to do, now we wanted to find a residuated lattice for these 5 truth values that would have this specific negation. So what is this negation capturing? Well, if something is true, 1, 1, 1, 1, 1, that's how we were interpreting the top value in the lattice. Negation should be false. I should move it to the bottom value, 0, 0, 0. And then all the other shades of false, because they still correspond to false when I negate them, they should become true, which is the top value of my lattice. Now, if you look into the literature, when one speaks of many-valued logics, the classical example, there are many reasons why the classical example is always given by intuitionistic logic. And if you look at the negation intuitionistic logic, it's not the negation we want. It's the dual. It's like flipping all the truth values. And we went through the literature for quite some time, and most work that people would have been done was based on intuitionistic negation. So, it took us quite some time to figure out how to proceed, what was the right residual lattice to use. And eventually we found a paper, quite recent at the time. At the time, this paper was like 5 years old, talking about dualizing intuitionistic negation. And the motivation for that actually came from the work that the Brazilian logician had done in the 70s, that 30 or 40 years later, they figured out how to do it better, and they had to dualize intuitionistic negation, and they figure out what was the right algebraic structure to do this. And this algebraic structure is called the Da Costa algebra in honor of that Brazilian logician. Okay, so now with the Da Costa algebra, we can define the semantics for this new logic that we call robust linear temporal logic. So how do we define the semantics? Through a valuation function. That's a function that takes a formula, an infinite string of sets of values for the atomic propositions. Now, if my formula is just an atomic proposition, the semantics is classical. I see if the atomic proposition is satisfied at the first entry of my string, and therefore I say it's true, otherwise it's false. And here I want to contrast these with many other approaches to define robustness in temporal logic, like in STL, where the robustness comes from the way in which atomic propositions are interpreted. Here they're interpreted classically, so that's not what we were doing. So any approach that constructs robustness by either interpreting atomic propositions, say on the real numbers or on a lattice, is orthogonal to what we're doing, and in fact can be combined with what we're doing. Robustness in our case will actually come from time, and that's already embedded in LTL. So for the Boolean operations, we just directly transform them to the operations in the Da Costa algebra. That's why you have to find the Da Costa algebra. And now what we have to define is what's the interpretation of the temporal operators. And if I look at the box operator, that in robust LTL, we put a little dot just to distinguish it, the interpretation is very similar to what I had before. Well, the top value corresponds to having always 5 satisfied. The value below corresponds to have eventually always satisfied, and so on and so forth. And for the eventually, there are only 2 things that can happen, either eventually satisfied or it is not. So the representation corresponds to eventually phi at all the bits on the truth values. So good. We came up with some definition for a new temporal logic. Now the question is, did we get something that's right? And how do we know if we get it right? Well, we're going to measure this in 2 different ways. Expressiveness, do we get interesting examples? And tractability, can we solve verification and synthesis problems, and how complex? Well, is it decidable, and how complex are they? So first, the formula we started to give to motivate all of this was box dot P implies box dot Q. And I talked about weakening the assumption and weakening the guarantee. Do we actually get that? And indeed we get that. To get the top value of in our logic for this formula, what needs to happen is that if always P holds, we need to guarantee always Q. But if we can always P to eventually always P, we have to guarantee eventually always Q. And if we further weaken it, we get the corresponding weakened guarantee, and so on and so forth. So yes, that we use as motivation is directly guaranteed by the semantics of the logic. I just write box P implies box Q, and I always have all these guarantees that as you weaken the assumption, you guarantee that you weaken the guarantee. You don't just fail catastrophically. Let's look at this other formula. It's a formula that appears in many papers, and that it says that every occurrence of P that we think as a request should eventually be followed by an occurrence of Q, which is a grant. Let's see what's the interpretation of this in RLTL, and this is what interpretation is. And what I would like to call your attention to is when we weaken, when we look at the truth values below the top, what we obtain is something that had also appeared in the literature in a completely unrelated way. And it appears so many times that it even has a name. The first one is called strong fairness or compassion. And the second one is called weak fairness or justice. So those formulas that appeared in literature in a completely different contexts are now unified. And now we have an explanation as to why people thought about this. They're just weakened versions of this formula asking that requests are eventually followed by occurrence of grants. So the fact that we captured these formulas that appeared in a completely unrelated nature in the literature, and now we give an explanation as to why they're useful, suggests that somehow the semantics we define is, a reasonable one. How about expressiveness? Well, every RLTL formula, when they define the semantics, we have this formula.
Paulo, can I ask you a question?
Yes, absolutely.
So, so you only have this 4 valued semantics because you only looked at LTL with always and eventually?
Very good question. So
there were 2 reasons. You said you have a result for full LTL. So if you keep on adding operators, you're gonna have more than 4, right?
So with full LTL, I still have 5 truth values. We write it like 4, but if you count the zeros and ones, it just ends up being 5. And the reason is the following, that we wanted to reuse every single algorithm that was developed for LTL. And that will then mean that the logic that we introduce has to be as expressive as LTL. And that's the reason why we cannot go beyond these 5. I can also define as semantics that we could have uncountable or countably infinite number of truth values. But then it becomes more expressive than LTL, and then the standard algorithms no longer work, and so on and so forth. So that was kind of by design.
I see. Okay, thanks.
What about nesting? If you would have nesting, would this increase,
no, even if you have nesting, you remain with 5 truth values. So the semantics we define for the general LTL, yes, allows for the nesting, allows for everything. So in terms of expressiveness, as I was saying before, we have these 4 bits. We can write an LTL formula for each bit. And this would then show that LTL and RLTL are equally expressible. Now, this also shows that the verification and synthesis problems are decidable because I can convert everything into LTL formulas. Now, the problem with this is that this translation incurs an exponential blowup. So if we follow this route, we won't really know what's the complex or intrinsic complexity of both verification and synthesis in RLTL because of this exponential blowup. So what we did was to try to solve this problem directly. And what we were able to show is that, yes, both verification and synthesis, they're decidable, but their time complexity is the same as LTL. And so here's a little table where we're comparing LTL with RLTL. And the only difference you see is that there's a 2 that gets replaced with a 5. And the reason for that is LTL is 2 valued. That's why I have a 2. And now we have a logic that is 5 valued. That 2 becomes a 5 because we need to account for those 5 truth values. And I say that the complexity is the same because I can always convert this 2 into a 5 by putting a constant multiplying the exponent. So this 5 becomes a 2, and then they're both, the complexity class is essentially the same. Now, interestingly, we can do even better if we focus on a smaller fragment of RLTL. We can bring the complexity of RLTL even closer to LTL. And we did this by understanding what are the operators in LTL that really give us trouble. And it turns out that it's the implication operator that tends to give us trouble. And so if we define a fragment of RLTL where all the formulas only have one implication, they're of the form phi implies phi, but neither phi or psi has an implication. In reality, we allow for certain kinds of implications, but to simplify, let's say there's only one implication at the top level. Then in this case, what we can show is that the complexity of verification is given by this expression here, where you have, if you want to think, a combination between being exponential with base 2 and being exponential with base 3. And what that k that appears there, it's counting the number of subformulas that have a box dot operator. So if there are no box dot operators, k becomes 0 and we recover the complexity of LTL. The more box dot operators we have, the more we're moving complexity from a base of 2 to a base of 3. In either case, now instead of the bound having a base of 5, now it has a base of 3. So it becomes even closer to the complexity of LTL. And now the other question is, okay, so this seems interesting, but this fragment, does it really capture interesting properties? Well, there's something called the Buki store, which has lots and lots of examples of Buki automata and their corresponding formulas. And so went to the store and we found that about 95% of those formulas can be written in this fragment. So from that perspective, this fragment is indeed interesting. And then we also looked at this challenge called the rigorous examination of reactive systems, where we're given systems and formulas. And we tried to write the corresponding formulas in RLTL just by putting these dots on the box individual operators. And we tried to see that if we solve those problems, is it the case that when we evaluate the problems, the formulas would have the top value in our logic and the bottom value? If that was the case, there's no need for our logic. We should instead be using LTL. Or do we have all the truth values in between? And they do have the truth values in between. For example, in 160 formulas that we analyzed, we saw that, for example, 14% of them would be false according to LTL, but the truth value was the second highest, meaning that even though they don't satisfy the specification, they're pretty close to satisfying the specification. So instead of doing verification with LTL, if we do RLTL, we actually give this information to the designer that specification is not satisfied, but you're very close to meeting the specification. And this can then be very useful to tweak the design and actually get it to the level that you want. And even for the formulas that are falsified, if you check them using LTL, we saw similar phenomena that they're falsified, but some of them, they're pretty close to being true. So again, showing that if you do verification with RLTL, you can give very useful information to the users. Now, the last thing we did was to do an empirical complexity of the overhead we have to do RLTL verification in this fragment versus LTL. Here's how we did that. So the theoretical bounds are 3 raised to the length of the formula for RLTL and 2 raised to the length of the formula for LTL. As I mentioned before, that 3, I can convert it to a 2 by having a constant on the exponent. And this constant is 1.59. So what we said was, well, rather than using these bounds, let's actually compute this constant empirically by doing examples. So I can determine that constant empirically by computing the running time that I need to verify formulas on a given system, and then computing that empirical value. And we did several examples. In these examples, the constant actually ranged from 1.016 to 1.058. So much smaller than the bound that we had there. And then if you plot these on a logarithmic scale, that constant is just the slope of this curve. And you're basically seeing the same thing, that the slope of this curve is very close to being 1, meaning that the overhead in running time compared with LTL for this fragment is fairly small. So it's, in summary, lots of formulas can be written in the fragment. If you use it for verification, the overhead in terms of running time is low, and you give very useful information to the designer because you give it much more detailed information about whether or not properties are satisfied in a robust manner, and even if they're not satisfied, how close they are from being satisfied. So I hope that I convinced you that robustness is an essential property of every well-designed system. RLTL is a convenient way of specifying and verifying and even synthesizing robust systems if you want. Why convenient? The syntax is so close to LTL that you can reuse every LTL formulas. And you saw us doing that. We just went to repositories and we just reused those formulas. And because the back engine of RLTL is based on algorithms that were developed for LTL, every time there's an improvement in LTL, we can reuse those algorithms to make a verification for RLTL even faster. Now, the synthesis problem here is relatively unexplored. We show that it's decidable, we have this complexity by using standard algorithms, but still we haven't spent enough time to see if we can develop customized algorithms or finding fragments for which the complexity of synthesis could be further reduced as we did for LTL. And with this, I would like to thank Radu for inviting me, my students and postdocs that worked together with me. You have here some references in case you're interested in looking at some more details, and I'll be happy to take any questions. Thank you.
Thank you very much, Paulo. Here is your applause. So I would like to mention that it was not only me that invited you, it was also Ružica, Ras, and Sanjit. So we all
absolutely, and I'd like to thank all of them. Thank you all.
And so now I take the advantage of the chair for this session to ask the following question. So Kalin had rules, he had an ordering among the rules. You have also an ordering. So can you take Kalin rules and write them in RLTL?
So he was using STL. So STL has an LTL, core built in there. So if we disregard how the atomic propositions are being interpreted, yes, we can write the rules here. Mm-hmm. And I'm sure that what we did from going from LTL to RLTL can be done from STL to RSTL.
Mm-hmm. But what if he had hierarchy? I mean, he had this ordering, and it was like 3 levels. But what if he has like 6 levels in his ordering? So you have only 4.
Yes. So yes. So that's a different question, because the ordering I have, it's intrinsic to the logic, in the sense that to define a semantics, you need an algebraic structure, and that algebraic structure in general, well, you also have logics where the truth values are not linearly ordered, but in our case, they're linearly ordered. I think in Kalin's example, this was not embedded in the semantics of the logic.
Yeah, of course. No, it came on top of this.
Right.
Paulo, really quickly, can you tell us, like in 2 sentences, how do you actually do verification?
Oh, for this fragment, when you do verification, first the question you pose is a bit different. It's not, is it true or false? One way of posing it is the truth value at least this? It's like deciding between being above this truth value or below this.
So you don't run like an LTL model checker 4 times.
We do, yes, we do. And then what we do in this fragment to make it more efficient is that we start with the lowest bit, and then we check the value of the lowest bit. If the value of the lowest bit is 0, there's no need to check all the other values. We already know they're all 0. If it's 1, we're uncertain, we move to the next bit, and we keep on doing like that.
Okay.
So in the worst case, we do 4 LTL verifications, or we invoke an LTL verifier 4 times.
So use it off the shelf. You don't construct yourself the bookie automaton.
No, I use off the shelf, and what I do is this interface where I grab my formula, decompose it, figure out which formula do I verify now, and what do I do next. So this was also by design, so that every time there's a faster verifier, I can then latch onto that and then make the verification of RLTL also faster.
And for synthesis, you said it's decidable. You just showed that basically you can reach some sets.
So for synthesis, we use the classical algorithm, which is you go to the Buki automata construction, and then you do a determinization and all of that stuff. However, we don't know how to optimize this process the way we did for this fragment for verification. There, we don't know how to optimize it.
Some other guy, you're going to have like a different acceptance condition for each of the LTL things?
So we have different types of accepting states. Yes, yeah. Exactly. And for each, so it's actually not accepting states, it's actually the initial states. We have 5 initial states or 5 classes of initial states, and runs from a different class will give us different truth values.
Okay. All right, so I see that Nekmia is getting a little bit nervous. So I would like now to give the opportunity to Ružica to introduce Nekmia. Ružica, are you there?